can now move on to systemic risk and systemic losses. The systemic risk is the possibility of widespread losses in the financial system due to shocks that originate in particular parts of it. So, how are those losses measured? There are several ways to do so. The first one consists in computing the total loss of bank equity, which is the measure of the ability of the financial system to extend credit. We could also consider the aggregated loss inflicted on the non-financial sector, defined as the total shortfall in payment from the financial sector to household and non-financial firms. The third one is the total loss in asset value summed over all entities in the system, which is called the systemic loss in value, and represents the total amount by which the value of all claims are reduced relative to their normal value. So, as you can see in the equation 16, if X represents a shock to the outside assets of the N financial nodes, and P the nominal payments due from this node to each other and to the external sector, then the first term represents the direct loss in asset value by the financial sector, and the second one is the measure of the indirect loss in value due to reduced payments. In addition, financial losses can have other consequences for the real economy, such as administrative costs and legal costs or bankruptcy. Uncertainty in shock sizes creates uncertainty in losses, so there is a need for a systemic loss measure with a probability distribution. The choice of the model to assess the systemic risk will have implication for the setting of policies that limit the contagiousness of the financial system. Network models to assess systemic risk generally assume complete information about interbank exposures. In practice, this information are never available to the public or even to the banks. In fact, even regulators do not have a clear view of the payment obligations between financial institutions, as they are always changing. Different solutions have been studied with the aim of resolving this lack of information issue. One of the numerous methods that have been developed defines networks through co-movement in stock prices. This methodology has exploited very abundant market data to identify institution links. This contrasts with networks assessing models that rely on information about payment obligation, which is generally confidential and available in low frequency. Several types of data have been used in these methods. Networks have been constructed based on the Granger causality relationships in stock returns, which has the advantage of capturing genuine spillover effects. It has been discovered that connectivity increases significantly before crisis. Changes in funding costs and the variance decompositions for the forecast error in multivariate time series have also been used in order to estimate networks for market data. So, what are the channels of contagion through which a shock can spread into the network? In a network where balance sheets of the different institutions are interlinked, the propagation can go pretty fast. Interbank claims shows itself as a good way to share risks between banks, but it establishes relationships facilitating the spread of a shock of bank issues. The notion of trade-off between the pros and the cons of interconnectedness thus appear, but we will talk about it later on. If we consider a downward shock to a bank's assets that is sufficiently large for the net worth to be unable to absorb it, the bank will be incapable to repay its liabilities. In other words, it will default. The actual payment of Bank I to the bank will be less than the initially promised payments. If the payment shortfall is large enough, it may lead to the bank failure. This chain reaction is called default cascade and shows how a shock can spread through the network. Another propagation phenomenon is the funding run. It happens when banks pull funding from one another and may be triggered, for example, by an unexpected liquidity shock. If the bank sees its outside liability reduced, it will have to reduce and to adjust accordingly its assets. Thus, if this implies reducing its lending to other banks, the latter will in turn have to reduce their lending. This is the chain reaction called funding run. Also, shocks can spread through common exposures that banks may have concerning outside assets. Thus, they may suffer correlated shocks. We can highlight two main mechanisms. The first one is the information contagion that happens when creditors make assumptions about an assets make assumptions about assets held by banks following the disclosure of information about the assets of one single bank. Secondly, when a bank is forced to sell its liquid assets, it brings the prices down. This will make an incentive for other banks to do so as well because of the price drop. This phenomenon is called fire sale. These mechanisms can happen even if there is no network, but they are amplified with interconnections between banks. An optimal portfolio selection allows firms to diversify their risk, but it can lead to a more vulnerable system if many different firms hold a similar portfolio of assets. The probability for the firms to be in financial distress at the same time will be higher. So, it is also important to assess the potential contagiousness of different banks, given their individual characteristics and their position in the financial system. Using just individual balance sheet information about a bank, it is possible to assess its inherent contagiousness and its inherent vulnerability to contagions. Pairwise measures have been developed in order to assess this vulnerability. So you can see the equation 18 on the slide. We can thus measure bank J's vulnerability to a shock that reduces bank I's outside assets, valued by the ratio 18. Wi being the net worth of the bank I, and lambda I the outside leverage of bank I. If this ratio is smaller than 1, we can say that bank J is relatively immune to a shock from bank I, but this does not guarantee complete immunity for bank J. The reason is that it does not take into account a shock transmitted from other nodes than node I. It is thus only a first-order measure of vulnerability. So another ratio has been developed, as you can see in equation 20. Here we consider J's maximum exposure to any given counterparty divided by its net worth. If this ratio is smaller than 1, the only way for J to fail is if more than one of its creditor banks completely fail or if its net worth is reduced due to a shock in its own assets. In order to avoid too high vulnerability levels, the Basel Committee put a limit to any single counterparty at 25% of the bank's Tier 1 capital. The pairwise approach can be extended in order to assess the vulnerability of subsets of banks to the default of one single bank. We consider that each bank is a node and define the financial connectivity of a node beta I. So as you can see in the equation beta on the slide. This is the fraction of node I's obligation that are owed to the financial sector. Beta I will have a tremendous importance in determining the contribution of each node to the systemic risk. From this assumption, we reach equation 21. The left part of this equation is the contagion index of a node. If this number is high, it means that the node contributes a lot to the systemic risk, in a sense that it is more likely to fail. Furthermore, this failure would have a large impact on the rest of the financial system due to its high financial connectivity. It is also important to consider the trade-off. So the double-edged nature of connectivity is an aspect that should never be undermined. While allowing the diversification of the risk for the different institutions, a growing interconnectedness allows shocks to spread more widely and easily into the network. It was found that an increasing connectivity increases shock transmission and also shock absorption. When connectivity is low, the first effect dominates the second, and the opposite when connectivity is higher. A highly connected network is more likely to know more severe crises, while a low connected network will know a higher number of crises. Volatility can be measured as the number of banks from which one other bank borrows. But it can also be measured as the size of a bank's interbank liabilities. Studies have been made to study the impact of a varying maximum number of counterparties allowed per bank, while the average number of lending counterparties per bank remained unchanged. We are thus in a core periphery system, and the higher the maximum, the more concentrated is the core. It was discovered that there exists a positive and non-monotonic relationship between the total number of failures and the maximum number of counterparties allowed when the system is shocked by the failure of the most interconnecting bank. A lower cap increases the size of the core and decreases the exposure between core banks. We can now move on to the conclusion. So the main issue that was discussed in this article was what the existing literature had to say concerning the relationship between interconnectedness and financial stability. Thus, growing interconnectedness allows a better risk sharing, or does it weaken the system by facilitating the propagation of shocks? This question cannot be answered yet without considering a lot of other factors. Many models have been developed in order to have a better understanding of these mechanisms, but more further research needs to be done in order to have accurate contagion measures. Also, there is still some work to be done concerning the relationship between financial losses of the supply of credit and their impact on the real economy. The article was focused on the dynamic of contagion in the financial system and found out another challenge for the research. This challenge consists in building more realistic models and get a better understanding of the incentives of the individual that develop this kind of networks. There is also the need to have a more comprehensive account of the different mechanisms that cause contagion within the financial system, as well as more research on phenomena like fire sales or information contagion. Finally, we found that it was difficult for us to criticize this paper because its main objective is to gather and to summarize the work that already have been done on the subject without really going deeper into the issue that was discussed. The article highlights the work that is yet to be done, but does not clearly bring something new, as it is not its purpose. Thank you for your attention.